Hello, and welcome back to another edition of Engineering Economics. I'm your professor, Dr. Johnson, and this is YouTube. In this video, we're going to be talking about sensitivity analysis, but first, in order to motivate that, I want to ask you a couple of questions. We're using the same example that we've talked about in the last couple of videos, so if you haven't seen those recently, take a moment, pause the video, and read the question, and then think about if we use an interest rate of 10% instead of 6%, would the break-even threshold for the number of miles we have to drive per year go up, go down, or stay the same? I'll give you a moment while I stare awkwardly at the camera. Okay, so if we use an interest rate of 10% instead of 6%, that effectively means that we are discounting future benefits more than we were before using the 6% rate. That means that because the benefit of the Yaris is in the future from the fact that we are saving money on gas and saving money on maintenance and get a larger salvage value at the end, that means all of those future benefits are now discounted more than they were before. And so to make up for that, we need to drive more. So the break-even threshold for miles driven is going to go up. Next, I've got another question. Same sort of setup, but instead of using the car for 4 years, suppose that we think we can get a useful lifetime of 5 years out of them. But this means that the salvage value for each car is going to be reduced to $250 from the Civic and $500 for the Yaris. If that's the case, would the break-even threshold go up, go down, or stay the same? Okay, so for the second question, it's hard for us to know without actually doing the math because there are a couple of things going on if we extend the useful lifetime. The break-even mileage goes down if the useful lifetime goes up because we're spreading out the benefits over a larger number of years. However, if the salvage value for each car is cut in half, that means we're reducing one of the benefits of having the Yaris. So that means the break-even mileage would go up. So we have these two different changes to the problem that are going to have opposite effects on the break-even point, and we need to know how sensitive that break-even mileage parameter is to changes in those other two parameters. That's why we need sensitivity analysis. If we have multiple things that are changing, we need to know which one is going to impact the quantity of interest more than the others. There are a couple of different ways that we measure sensitivity, but the most common is what's called elasticity. This is the proportional change in the output value that's caused by a proportional change in an input parameter. In other words, if we change the input parameter by 1%, what percentage change in the output value occurs? With the previous example, we would say something like we want to calculate the elasticity of the break-even mileage with respect to the useful lifetime. That's how we would talk about this. Elasticity allows you to make more of an apples-to-apples comparison because it's associated with perturbing that input parameter by a similar amount, proportionally speaking. We could take the derivative of the output if we have an analytic function describing the relationship between the input and the output, but that's going to tell you about the absolute change caused by a unit change of the inputs instead of a proportional change. So if we scale the input and the output proportionally, that is going to give us that apples-to-apples comparison. The output that we're going to choose to do a sensitivity analysis on is usually going to be some sort of decision-relevant parameter, something that we choose or that we have a good idea of what the value actually is going to be. In this example, if you are a student at Purdue, you probably don't have to drive very much, Maybe you have a really short commute if you live off campus, but generally speaking, maybe you drive to Chicago or Indy on the weekends sometimes, but during the week, unless you have to go out for groceries or something along those lines, you probably don't drive very much. And so the mileage that you would drive per year is going to be very different now than once you graduate and get a job, maybe in a bigger city where you have more of a commute, or if you're living out in the suburbs somewhere and you have to drive in to work, then that decision is going to change depending on your circumstances, but you probably have a decent idea of what the value is going to be. That's why we would want to know what's the break-even mileage per year with respect to some other input parameter to our model that's going to be more uncertain. We need to know, how is the break-even mileage change depending on how long the car is going to last. That's more uncertain than our own driving habits or the average price of gas over the next 4 or 5 years. That's a lot more uncertain than our driving habits. So we want to know how sensitive something is that we have control over with respect to changes in things that are more uncertain and that are less predictable. Even with this pretty simple example, we have a handful of different input parameters that we could examine. And for each of them, we could check how sensitive the break-even mileage is with respect to those different parameters. The way that we're going to summarize all of this information is something called a spider plot. That's how we're going to visualize how the particular output, in this case the break-even mileage, changes as a function of proportional changes to independent input parameters. The proportional changes allow us to plot the results on the same axis. So on the x-axis, we don't have to plot a useful lifetime of 4 years, 5 years, 6 years, and so on, but we're going to rescale everything with respect to our most likely estimate, in this case for the useful lifetime 4 years, and we're going to see how the break-even mileage changes if we have a percentage change in those input parameters. In this example, we can focus on a number of different variables, including things that we talked about in the clicker questions at the beginning of the video, like the interest rate or the useful lifetime or the price of gas, but we also have uncertainty about the actual mileage that we're going to get for the Yaris because we don't own it yet. We haven't driven it. We don't know exactly if it's going to get the mileage that the manufacturer claims. We also might have O&M costs that are more or less than we think. Here's what the spider plot looks like. This is what we're going to learn how to make in the next video in Excel. But what you can see is that on the x-axis, we have a proportional change to some input parameter with respect to the baseline most likely estimate that we have for that parameter. So the 0% line here, this is going to represent our best estimate for the value of each of these input parameters. And then we perturb it by anywhere from 20% less to 20% more and see how the break-even mileage on the y-axis changes in response. For example, we can look at this aqua-colored teal line, and this represents the O&M costs predicted for the Toyota Yaris. What we can see is that if we increase it by 5% compared to its baseline value, then we get an increase in the break-even mileage from around 8,000 to about 9,000. We don't necessarily know how that compares proportionally unless we're going to calculate it. So if we want to make this a little bit easier to understand exactly how sensitive it is and relate this back to the elasticity concept that we talked about, we can also rescale the y-axis as a proportional increase or decrease in the break-even mileage. Now it's really obvious to see that if we have a 5% increase in the O&M cost for the Yaris, that's going to relate to about a 15% change in the break-even mileage. What we can also see here is that this means that some parameters are obviously more sensitive than others in our model. The O&M cost, because it has a steeper slope, that means that the break-even mileage is more sensitive to that parameter than, for example, the price of gas, which has a smaller slope. We also want to look at this plot and make sure that the intuition is understandable behind each of them. So we should expect, if we have an increase in the positive quadrant here for the O&M costs, or in yellow, the interest rate, that means the break-even mileage is going up compared to our baseline estimate. That corresponds with our intuition that says if the interest rate increases, then we're discounting future benefits more than we were before. Therefore, we need to drive more in order to make up for it. Or if the O&M costs are larger than expected, that means we need to drive more in order to get more benefit from the gas savings compared to the O&M savings, which are shrinking as the O&M goes up. On the other hand, if we have something like the useful lifetime, if that increases, that corresponds to a reduction in our required break-even mileage that we have to drive per year. So this conforms with our intuition, and in the next video, we'll learn how to make this plot.